Traditional HDFS clusters are limited by the physical memory of a single NameNode, creating a hard ceiling for how many blocks the system can track. It is a common misconception that this bottleneck is driven by physical data storage capacity or the limits of the data nodes themselves. The real constraint is the metadata. In a monolithic namespace, one NameNode must store the entire file system map in its local RAM. Research conducted at Royal Research shows that as organizational data scales, these monolithic namespaces inevitably become single points of failure, crashing once metadata volume exceeds the NameNode's memory capacity. To scale storage beyond the limits of a single node, the architecture must be restructured through Hadoop Federation. In the Hadoop ecosystem, a namespace is the file system structure that defines the hierarchy of every file and directory in the cluster. This diagram represents the traditional HDFS model, where a solitary NameNode sits at the top of the hierarchy to manage the entire namespace. Physical storage capacity is increased by adding more data nodes to the bottom layer, allowing the cluster to expand horizontally. However, every metadata request, from file permissions to block locations, must route through that solitary NameNode. This line graph illustrates the problem. As the number of files grows, the metadata processing load eventually exceeds the NameNode's compute and memory limits. Adding more physical storage servers actually hastens this failure, as each new block generates more metadata for the central NameNode to track. When this single point of failure is overwhelmed, the entire cluster becomes inaccessible. Total system capacity is dictated by the narrowest architectural choke point, making monolithic namespaces incompatible with massive data environments. Hadoop Federation resolves this by integrating multiple independent NameNodes into a single cluster. The structural shift involves removing the single master node and distributing the management load across a horizontal plane of independent NameNodes. Each NameNode manages its own specific isolated namespace, operating with complete independence from the others. This enables a separation of concerns. Incoming traffic is routed to specific NameNodes based on the application or data type, rather than hitting a single hub. This ensures that a high volume of metadata operations in one namespace does not impact the performance of other applications in the cluster. By dividing the global metadata burden into localized fragments, the system eliminates the latency spikes associated with a single node bottleneck. Wide-scale growth is achieved by decentralizing the metadata map, allowing the control plane to expand alongside the physical storage. Federation moves resource management away from a monolithic approach toward a targeted strategy. On this management dashboard, administrators can allocate specific compute and memory resources to individual NameNodes based on their unique workload requirements. If one namespace experiences a massive spike in data processing, it remains isolated. The other NameNodes continue to operate with green-level efficiency. Beyond performance, this architecture significantly changes the security profile of the cluster. Because namespaces are independent, administrators can apply namespace-specific access control policies, represented here by the digital padlock. This granularity allows organizations like Royal Research to isolate highly sensitive data from the broader cluster, reducing the overall attack surface. The final benefit is the systematic isolation of failure domains. In a federated setup, a hardware or software node failure is contained within its specific namespace. While one namespace might go dark, the remaining federated NameNodes and the vast majority of the cluster's data stay online. This structural transformation ensures that a localized error in one section no longer results in a catastrophic global outage for the entire system. Successfully deploying Hadoop Federation requires a clear architectural plan for how data is logically grouped. The first strategy is planning namespace distribution. Data and applications must be organized so that workloads are balanced and easily accessible across the nodes. High availability is maintained by pairing each active NameNode with a standby node, as shown in this topology map. If an active federated node fails, the standby node immediately assumes its traffic routes to prevent data loss or downtime. The second strategy involves maintaining dynamic load balancing across the entire federated cluster. This load balancing router acts as a traffic cop, distributing data requests to prevent any single federated node from becoming an isolated bottleneck. This requires continuous monitoring tools to track the health and processing throughput of every individual node. Ongoing performance tuning then allows the system to adapt as external data loads change over time. Federation is not a one-time setup, but a continuous strategy of proactive load management and failover planning. This architectural schematic summarizes the shift. Hadoop Federation moves HDFS from a monolithic model to a decoupled multi-namespace system. This architecture facilitates horizontal scalability and more precise resource utilization across the entire data environment. It offers defensive advantages through isolated fault tolerance and namespace-specific security. Expanding physical storage capacity is ineffective if the metadata architecture lacks the overhead to map those new blocks. Implementing Hadoop Federation, supported by rigorous failover strategies, provides the necessary foundation for managing massive data environments at scale.